exponential growth and decay. Do not forget to subscribe, and if you have any question about exponential functions, you should watch this video before continuing. Exponential functions are used to model real-life situations in many branches of science and commerce. We will see some examples of modeling exponential. Common applications include compound interest in biological modeling. If a quantity grows by a fixed percent at regular intervals, the pattern can be described by the function. A is initial value. R is growth rate, usually represented as a percentage. Let's see how it works. During a locust plague, the area of land eaten is increased by 25% every week. The size of the area initially eaten is 1,024 hectares. Write a function A to model the area of land eaten after 2 weeks. Use the function to find the size of the area eaten after 3 weeks. How long would it take for the area eaten to reach 3,125 hectares? The initial area is 124 hectares. The rate is 25%. Take the formula for exponential growth and change the values. Time is 3 weeks. Take the formula and replace t with 3 and perform the calculations. Now take the formula and replace A with 3,125 and perform the calculations. This is an exponential equation. Time is 5 weeks. If a quantity decays by a fixed percent at regular intervals, the pattern can be described by the function. A is initial value. R is decay rate, usually represented as a percentage. Let's see how it works. A container of boiling water is placed in the refrigerator and its temperature is decreasing by 16% every minute. Write a function t to model the temperature of water after 10 minutes. Use the function to find the temperature after 5 minutes. The initial temperature is 100 degrees Celsius. The rate is 16%. Take the formula for exponential decay and change the values. Take the formula and replace t with 5 and perform the calculations. The number E. The number E is called Euler's number. The number E is used when modeling continuous growth that occurs naturally, such as populations, bacteria, and regenerative decay. In these types of problems, the number E is the best possible base. Look at the example. A culture contains 1,000 bacteria initially. After 1 hour, the bacteria count is 2,000. Write a function n to model the population growth. Take the formula to exponential growth and replace A with 1,000. And if the number of bacteria doubles every hour, the rate is 100%. Replace R with 1. So after 1 hour, we know the count is 2,000 bacteria. Now we will study this problem more precisely. The bacteria do not wait until the end of the 1 hour and then they all reproduce at once. The bacteria will continue to grow for a period of 1 hour, producing new bacteria that will also grow. Suppose we want to make the same problem, but now we want the rate per minute. So we take the rate and divide it by 60 because 1 hour has 60 minutes. And after performing the calculations, we get this formula. Suppose we want to make the same problem, but now we want the rate per second. So we take the rate and divide it by 3,600 because 1 hour has 3,600 seconds. After performing the calculations, we get this formula. We should notice that the base increases as the interval between compoundings in an hour decreases, and you should notice that the base converges on a value. This value is called E. It appears that rounded to 6 decimal places. However, the number E is an irrational number, so we cannot write its exact value in decimal form. The number E is defined as the value that expression approaches as n becomes large. Now let's rewrite the formula of exponential growth using the continuous growth rate. Pay attention. R is the continuous growth rate. To find the continuous growth rate, we take the previous formula and equate it to the new formula. After simplifying, we should solve this equation to find the continuous growth rate. The continuous growth rate is 69.32%, and the new formula takes the form